Well, thank you very much. Are you able to hear me at the back? Okay. I got all these awards, but you have to realize that they give a Nobel Prize to one person, and there were 273 authors on our papers. One of them was here a few minutes ago, and that's Tony Noble, who's the director of the Institute. And it really is people like that who did all this work, and I'm just trying very hard to represent them. So the things I'm going to tell you about today are things that are done by very large collaborations, and it's those collaborations that whose granddaughter should be saying, gee, they're smart too. Notice it's the granddaughter who said that, not my colleagues who said that. Anyway, we'll try to cover a few topics today, things that are a little bit different from what you're used to thinking of in terms of astronomy. Now, we're going to go and see a telescope later on that is looking at light from the things you see here, you know, stars and the sun and far distant parts of our galaxy, which are at enormous distances. That's one with 24 zeros after it, meters far away to the edges of the universe as far as we can observe. In fact, it's further than that to the edge. But we also, in doing measurements with unusual things, which I'm going to use as an example today, neutrinos, which are the smallest particles we know. They only interact with something or hit something if they come within 10 to the minus 18 meters of that something, which could be perhaps the nucleus of an atom or an electron going around it. In other words, 0.00018 zeros 1 meters. And so the scales over which we are studying things are from the really enormous down to the really tiny. Neutrinos are unusual particles. They are emitted in various nuclear reactions where nuclei come together and fuse and produce these neutrinos, or certain radioactivities that happen here on Earth. They, along with the electrons and the quarks that we think are the things that make up the protons and neutrons that are inside the nucleus of an atom. That's what you'll learn in your school. Usually you don't get in school or until you get to university to the point where you're talking about quarks. But the basic building blocks we think are neutrinos, quarks, and electrons. And we made measurements that determined basic properties of neutrinos that hadn't been known before, because they're extremely hard to detect. They only stop, as I said, if they hit the middle or one of the electrons going around an atom. And therefore, for them, matter is essentially open space, which is great if you're trying to use them to study the center of the sun, but not so great if what you're trying to do is to make a measurement. And here is what we had to build. It's the size of a 10-story building. It is the SNO, or Sudbury Neutrino Observatory. And this is a person to scale. This is, as I say, about 34 meters high, so it's the size of a 10-story building. In the middle is the material that gives us bursts of light for neutrinos from the sun 1 an hour. Now, if we had done this on the surface of the Earth, we would have had that as a problem. The cosmic rays that make the atmosphere glow and create those beautiful northern lights that we're so proud of here in Canada would have done the same thing in our detector. But by going 2 kilometers underground, which is where we do these experiments, they are reduced by a factor of about 10 million. So we are able to see 1 burst of light an hour without anything else interfering with it. In order to do that, we went down in the Creighton mine, owned by Vale now, previously by Inco, to a site that we prepared specifically for this experiment, which has now been expanded to what is referred to as Snow Lab. And there are many other experiments happening here. In fact, I think you had a presentation on dark matter recently, one of your, the last one, in fact, right? Tony Nobel was the one doing the presentation. And that is a lot of what is studied in the new section of SNOLAB. But we also have a recycling, if you like, of this detector. We call it SNO Plus, and I'll tell you a little bit about that as well as to why we wanted to do that. And so, really, by making these extra measurements and combining it with what's known from astronomy, particularly optical astronomy, we're able to study, well, in this case, we study with neutrinos, the center of the sun. How is the sun burning? Because when the sun burns, it makes neutrinos. They get out easily, and we detect them in our detector here. We also study with the dark matter what holds the Milky Way in the shape that you see it. It turns out there's just as much interesting stuff going on in between the stars as there is in the stars themselves. In fact, about 5 times as much mass. And that's a very important topic in terms of understanding overall how our universe is composed and how it evolved to the state it is today. With this new SNO Plus detector, we can even study 600 kilometers down into the Earth, because the radioactivity that exists in the Earth also produces neutrinos. Very difficult to understand that with any other approach scientifically. So, what about these neutrinos? They're not the sort of thing that you will encounter in your everyday life. I've already said they are the basic particles that we don't know how to subdivide any further. Scientists are always very careful never to say this is the absolute truth. We say this is as much as we know so far. If we'd been talking back in let's say 1850 anyway, about how the world is composed, we certainly wouldn't have had all of these things. In fact, before about 1930, neutrinos would never have even been mentioned. But this is what we think today. We have a model that seems to work extremely well. We have 3 types of neutrinos. We call them flavors, just for fun. You'll never taste one, but that's nevertheless the whimsical way that physicists and astronomers kind of like to deal with things. I've already mentioned that they can pass through matter with no problem. They can pass through 10,000 billion kilometers of lead with only a 50% chance of hitting something. Now that's the distance that light travels in a year. So you can imagine just how big a distance that is made of lead, because that's what it takes before they happen to hit something inside the lead. So when we're talking to younger audiences, we often say neutrinos are kind of like a superhero. They can go through anything. They don't mind the intense heat at the center of the sun. In fact, they're born there. That's their home. And so neutrinos are unusual particles. If you can manage to detect them, then you can do very, very fundamental things. And the things that you can do from the neutrinos that are produced in the core of the sun can tell you a lot about the sun, but also about neutrinos themselves. So if you've wondered, what is it that keeps the sun burning for all of these years? It's nuclear reactions where gravity compresses things and heats it up to the point where the atoms, in fact, the nuclei of the atoms that hit each other are going so fast that they can penetrate inside each other and fuse together. And when that happens, in many cases, there are neutrinos produced. There's an enormous number of neutrinos produced in the core of the sun continually. In fact, right now, for each of you, there are billions of neutrinos per second going through your body. And those neutrinos you will never notice. But once in your lifetime, one neutrino will actually hit something in your body. It'll change that atom it hits into another element, and you won't even notice. Unless, of course, it happens to hit you in your eye, and your eye is closed, as many eyes often are by the time I get to this point in my talk. In that case, you might see a little tiny burst of light, the way we see them in our detector. We have a detector that's kind of like the ultimate eye you can imagine. a lot of light sensors looking in at a place where neutrinos can hit the central target. In fact, somebody estimated that with this, without other background light, you would be able to see a candle on the moon. It's that sensitive. So we try to detect these neutrinos that are heading for our detector underground in Sudbury. So it kind of goes like this. In the center of the sun, two nuclei fuse together, they produce a neutrino. This neutrino happens to be the one that's, or one of the ones that's heading towards Sudbury. It goes through the solar system, and there it goes on its trajectory towards Sudbury and our detector, past our surface buildings, past the ore body in the mine, and heading for our detector down here, and boom, you get a burst of light once an hour. And so that's the process we're looking for. And it's very different, as you can see, from what astronomers are doing. It's not that different. It's just that it happens that they're using light photons rather than neutrinos and looking at the light that objects produce. If you look at the sun, you look at the surface. When we look at the sun, we look at the core of the sun. And so what we're doing is very complementary to what astronomers are doing. And it's become part of what is these days being called multi-messenger astronomy that I'll mention at the end of the talk. It's rather neat that we now have a variety of ways to do astronomy and astrophysics other than just looking with light. And we're learning a lot in the process. What we found is that the neutrinos behave in a strange way as they're on their journey from the center of the sun to us. This is a drawing actually that the Nobel Prize people put up on their website. There's Captain Neutrino in their version of him. And it turns out as he moves along on his trajectory, he switches from his electron suit, sometimes his muon suit, and sometimes his tau suit. In other words, neutrinos actually change their identity on the way from the sun to our detector. And this is something that fooled other experiments before we made our measurements, because the other experiments were only capable of observing electron-type neutrinos. And so they found too few, which we did too when we studied just electron neutrinos. But it wasn't known whether that was because the calculations of how many there were being produced in the sun were correct, or maybe those calculations were off, and therefore they thought they were observing too few when really there were just too few being produced. We had a material called heavy water. And heavy water, 1 in 6,000 of the molecules of water that you drink every day are heavy, though that molecule is heavier than the other molecules because there's an extra neutron inside the nucleus of the hydrogen in it. Normally there's only a proton there with a positive charge. A neutron with no charge doesn't change the chemistry, it just makes it heavier. And so it's called deuterium. And so it's D2O instead of H2O. And it turns out Canada had a fair amount of deuterium because it's non-radioactive, but it's used in the Canadian style of nuclear reactors. And therefore we were able to remarkably borrow $300 million worth of this type of unusual water while they were waiting to build the next set of reactors. By doing these measurements where we measured all neutrino types with heavy water, as well as measuring the electron neutrinos that had come to the Earth, we found that of all the neutrinos, only about 1/3 were still electron neutrinos. It was clear evidence that 2/3 of them were changing into mu or tau suits before they got to our detector. And so that really, along with this, is what the Nobel Prize was awarded to our collaboration for, because we were able to verify that the solar calculations were extremely accurate. It's quite amazing what was done by the people who were calculating how the sun burns. But to do this, as I showed you in a small scale before, we had to build this unusual detector. At the center of it is 1,000 tons of this heavy water, valued at $300 million and on loan for 10 years for $1. $1 million a year insurance, but but that sounds pretty good as a deal. It was pretty good as a deal. The Canadian government really served us very well, and so did INCO and now Vale, and they are continuing to do so. It is in the middle of a very big, 12-meter diameter, acrylic container. It's only 5 centimeters thick, and it was put together from 120 pieces that were small enough to go down in the mine cage that you use to get down into the mine. We'll see that at the end of the talk, what it's like to travel in that mine cage. Surrounding this central region here and this transparent acrylic sphere are 10,000 light sensors that look in at it and are connected to computers by cables on the outside in a bath of highly purified regular water in a liner produced by, the idea, the concept for it was developed in the mining engineering department here at Queen's. And so in the middle, we had very low radioactivity. We purified the water in that region extremely highly, and also the water out here. In fact, Tony Noble was one of the principal people responsible for accomplishing this, he and David Sinclair at Carleton University. The water in the center is 1 billion times purer than ordinary water in your tap. It really took tremendous effort to get that so pure, and we did it so that we would not interfere with our measurements, so we could make clear measurements of both the electron neutrinos and the total number of neutrinos using the heavy water. And we also had to keep everything else very clean, because small amounts of radioactivity could interfere with our measurements. And so everybody who came to work after we got this liner in place took a shower and put on lint-free clothing, and this was a clean room, cleaner than an hospital operating room in the central area for people to work in. And when we were finished, even though it's a very dusty, active mine, they're still taking thousands of tons of ore out of the mine. It's a very, very active and valuable part of Vale's work. We had less than the amount of dust you could pile on your thumbnail on the entire detector. And that was necessary in order to be successful in the experiment. It was a major engineering task as well. And here you can see people, give you the scale. These are people dressed in their lint-free clothing. Here is where the acrylic sphere was being put together in its last phase. There's the light sensors you can see looking in here. In this case, they were still covered over with garbage bags, conveniently set up so that you could have a string attached to it, and when you were finished, you could pull the garbage bag off and have it clean in the meantime. And here is after the garbage bags come off. It was eventually closed up completely, and cables from every one of these 9,500 light sensors went up to the surface to our computers, and we could thereby see the pulses of light that came and distinguish them from radioactivity. You can see the very complex systems that Tony and his co-workers created in order to do this high purification. In fact, you can see also this is the region where heavy water was being dealt with, and it was a contained region with a boundary around it because it was so valuable. If we had any leak, we wanted to make sure we had it. This is David Sinclair describing to Stephen Hawking how this system worked. Stephen Hawking visited us twice. He was very interested in the science that we could do with this measurement, and an amazing individual. We couldn't have him take a shower when he came down, and so Inco built a special rail car, and we vacuumed him and his wheelchair off completely above ground, put him in the special dust-free car, and he came down. And he visited us again in 2012, and I'll show you a picture of that as well. This was 1998 as we were starting. Now, I told you a lot about neutrinos and everything else, and sometimes I have the feeling I'm conveying information, but I'm not sure that I actually am. And in fact, the week of the Nobel Prize, I was on TV and radio and everything else telling people about neutrinos changing from electron type to muon type and so on. And so midway through the week, I get a call from This Hour Has 22 Minutes saying, we've been listening to you and we've made up a script. And do you mind participating? Because we've had a little bit of fun with the whole thing. And so just in case you think you're getting the message across, maybe you can think twice. So I'm not sure if I got the message across to this audience, but if not, there is an alternative to understand it, and it's a very Canadian alternative. So listen to this. So I even play this when I go and give a serious scientific lecture. I was at 3 places in Chicago last week, and I said, you in the audience who go out and give lectures to people, you may think you're communicating, but it's not necessarily true. Anyway, as they say, but seriously, why should you care about what we did? You know, it's pretty esoteric stuff. I mean, granted, you know, you are understanding how the world works at a very, very basic level. The laws of physics at a very fundamental level works extremely well for other particles, but not quite for neutrinos. And you might expect that scientists feel, oh, heck, it doesn't work for neutrinos. Instead, the idea is it's not complete. And we knew it was not complete because, for example, it doesn't include gravity. And so, in fact, we think that the properties of neutrinos may be a way for us to understand some things that are still fundamental puzzles in how the universe has evolved since the Big Bang. And so people actually welcomed the first bit of physics beyond the standard model as a way perhaps of learning more about our universe. And that's kind of the way scientists work. They find something new and they find something that's a little different from what they think is what's happening, and they relish it actually, and you can follow it up. And I was at Fermilab last week. They're doing nothing but neutrino physics at Fermilab. And that's the biggest accelerator laboratory in the United States. They're producing neutrinos and studying their properties. Anyway, I mean, what we did with the SNOW project is interesting in several ways, even from a practical way. You know, here on Earth, they are attempting to confine the sun in a magnetic bottle. Basically, they get it hot, like the center of the sun. You may have noticed 15 million degrees in the center of the sun. In their magnetic bottles, they want it even hotter, 100 million degrees. But the problem is that if that hot a plasma touches the walls of the bottle, it just melts it, and the stuff gets in the middle of the plasma and it doesn't work anymore. So the big effort is to try to do the engineering to have every particle that tries to get out get bent back in by a magnetic field so that you don't touch the walls of the bottle. But in terms of what's happening in the middle, we now know within about 10% how the sun burns from the measurements we've made. Slightly different nuclear reactions here, but very similar, involving deuterium. The reason this is interesting in terms of a potential power source for the future is that 1 in 6,000 of the water molecules you drink every day is D2O. And think of the inexhaustible source of energy you have if this can be harnessed. And so we've done a measurement that confirms the basic physics. It's now a major engineering problem to try to get a tremendously good source of power for the future. And people have been trying for a long while and are still trying. We're still, well, right now, the first one, this International Tokamak Experimental Reactor in France is expected in the next 10 years or so to be the first time that they get more energy out than was put in. But the other thing is, you know, those nuclear reactions that are powering the sun, they continue, and they continue in other stars. Hydrogen combines to form helium. Helium combines to form lithium, then beryllium, boron, carbon, oxygen, nitrogen. It's a whole sequence of production of the elements from which the universe is formed. And particularly the carbon, nitrogen, and oxygen from which we're formed is produced in stars similar to the sun. It turns out that if you do the calculations and you understand what's happening and how these stars burn, these days you can predict the abundance of all of the elements up to iron within about a factor of 2. Beyond that, it gets more complicated. But being able to predict the way in which the world is composed within a factor of 2 for the majority of the lighter elements is quite amazing. And for me, it's essentially a DNA footprint of where we came from. We are made of stardust. There's just no question about it. And stars like the sun in the first place, and eventually other stars blowing up, and then that material being combined in stars that go forward, we have a really remarkable picture of where we came from. And this is proving that we know how the sun burns to that degree of accuracy is to me an important part of confirming that that is the way in which we evolved. So let's talk about the Big Bang. So, oh, not that Big Bang. This Big Bang. On the other hand, that Big Bang was kind of fun. My other son, Fraser, and I, and Fraser came with me, and he and his wife came with me, and we were invited by David Salzberg, who was the technical advisor to the Big Bang theory essentially throughout the series. The equations that you saw on the blackboard and in the Big Bang theory were correct. He made sure that they were correct and also fed in slightly kooky but almost right bits of science for them to be pursuing as well. So it was kind of fun. We got to watch a filming. I didn't get to appear, of course, but got to watch a filming. He invites in the geek of the week, a legitimate scientist, to interact with the writers. They film it in front of a live audience, and if they don't get a laugh for one of their jokes, they rewrite it on the spot and refilm it. And so, well, I didn't have any input whatsoever on any of the programs you saw, but it's kind of neat. It's just as well that that program has gone off the air so that our friends don't compare us to Sheldon or Leonard or anybody else, but anyway. But the Big Bang, the real Big Bang theory, has an awful lot of supporting evidence these days. And I'm going to give you just a flavor for it, just to show where the things we're doing in the future will help us understand this more completely. There's a tremendous number of beautiful astronomical measurements made with telescopes on Earth, and now telescopes flying in satellites where you get above the atmosphere and you get rid of the twinkle effect that is caused by the atmosphere. But also particle physics is coming into this very well as well, because the model is that there was an enormous explosion about 13.5 to 15 billion years ago with a tremendous expansion thereafter. There was so much energy in that initial explosion. You see this temperature, 10 to the 27 degrees Celsius. In a very short time after the inflation, as they call it, you had the bare particles, electrons, quarks, and neutrinos, as far as we know right now. But also, every particle we've seen in particle physics experiments has an antimatter particle, such that if that antimatter particle finds a particle that's equivalent to it, for example, if a positron, which is the antiparticle for electrons, finds an electron, it converts it into pure energy. And so this is very valuable in positron emission tomography, because in positron emission tomography, there are certain radioactive sources that give out positrons. You can inject them into your bloodstream. They go to a place in your body you're interested in, tumor, or very often it's the head that people are trying to study with this. When a positron finds an electron, it converts into pure energy, but it's at rest typically when it finds the electron. And so off go two gamma rays, two high energy photons of light in each direction. And they go off exactly opposite to each other, because then on average they're at rest. And that's what has to happen, conservation of momentum, as we call it in physics. So the way in which positron emission tomography works is you have a bunch of detectors around, let's say, someone's head. And when two detectors go off at the same time, because these two gamma rays went off at the same time, you draw the line, and then another line, and then another line, and another line. You can actually observe where that radioactivity went. And so that has turned out to be a very valuable medical thing that's of interest to me, because my master's degree thesis back at Dalhousie in 1965 was about the properties of positrons as they annihilated in metals. Positron emission tomography came along 10 years later, after a lot of basic science had been done to understand positrons. But why am I telling you this? It's because what we think was happening in the Big Bang is the opposite of this. We had a lot of energy. We produced equal numbers of electrons and positrons. And we've seen those things, and that happened in experiments as well. A gamma ray can actually end up producing electrons and positrons. And that's what happens back here, along with all the other basic particles. So you start out with equal amounts of positrons and electrons, for example. But we don't see positrons. We're all made of electrons. And so one of the big questions that we're trying to deal with as we go forward is, where did all the antimatter go? This is a matter-dominated universe. And so that's one of the things that we are looking for information about, and it's something that we will look for in SNO+, because we're looking for a rare process called double beta decay that may give us part of the answer as to whether neutrino properties are what produced that in the early universe. So we got the basic particles produced back way shortly after the original Big Bang. After about a microsecond, 10 to the minus 6 seconds, it's still very hot, then you end up with the quarks combining to form protons and neutrons, because everything's expanding and cooling off subsequent to that. After about 3 minutes, the protons and neutrons form nuclei, and after 300,000 years, the electrons actually join up with them and form actual atoms. And at that point, it was possible for astronomers with beautiful experiments to measure what's called the cosmic microwave background. It's light, but it's cooled off now at this point to about, the temperature of the particular radiation is about 2 degrees above absolute zero. And what they were able to measure with these beautiful measurements is whether there are any variations in how uniform this is. And what they find is very tiny variations. But there's further theory. For example, the theory that another Canadian, Jim Peebles, received a Nobel Prize for this year. He's from Manitoba, from St. Boniface. Turns out all of the Nobel Prize winners in physics in Canada came from towns of less than about 40,000, at least when they were born. It's a small town phenomenon in this country, at least. But we've had 3 physics Nobel Prize winners in 5 years. It's pretty remarkable, as is Donna Strickland, the other winner in the interim. But anyway, he came up with a theory for how studying that cosmic microwave background can then result in, eventually, the formations of stars and galaxies. And then, now, we think it's about 13.5 billion years later, we have the world as we see it. But in order for that to happen, there are 2 things that contribute to it. One is the mass of neutrinos, and the other is the mass of the dark matter particles that you heard about last week from Tony. And so we are interested in what the absolute mass of the neutrino is. We know that it has a mass, and we know some details of the differences between the masses. We don't know the absolute value. And so what we're trying to do with the SNO experiment is a new experiment called SNO Plus. It's led by Mark Chen, one of the professors here at Queen's, and it is reconfiguring the SNO experiment. The heavy water has been sent back, and we didn't have to pay anything extra. We just gave it all back to them, and whew, $300 million bucks. We didn't lose any. But now we're filling the center of the detector with a material called linear alkyl benzene. It's called a liquid scintillator, and it gives 100 times as much light as the heavy water did. And so what you do is, first of all, it's lighter than the surrounding water, so you have to hold this central sphere down with these red ropes, and they had to be put in ultra clean conditions. That's all been done, and in fact, this is a picture taken Thursday. And there is, above the water level, liquid scintillator, which floats on the water, of course, and slowly the water is being sucked out from the bottom and taken out, and the liquid scintillator is being put on top of it. With this detector, we will study other lower energy fusion reactions in the sun because we have more light output, and we will also study this unusual process called double beta decay, where you have to have very low radioactivity in order to make the measurements. And that's in progress, and it's very nice to have an ongoing effort, because the original experiment cost about $70 million. And so we are now proceeding with something on the order of 15% of that in the add-on in order to do this next very fundamental measurement. This is all in SNOLAB. And SNOLAB was added to the original area where we had SNO, starting in 2003. David Sinclair was the original director of this, and Tony was the first operational director of it. It was built in order to attract the world to come and work with Canadian scientists, and that's really happening. You can see the set of different measurements that are being made. You will have heard about a number of these from Tony last week that are studying dark matter, and we're also looking for a signal from neutrinos if a supernova goes off in our galaxy. It's a very active place. It's very clean, like the original experiment was. It's deeper than, there's one other laboratory in China that's approximately the same, but the world is making its way towards SNOLAB for these future high sensitivity experiments. Very clean. You can see the floors. Back when I was responsible for SNO, which was roughly the same as that, my mother came to visit actually, and looked at that and she couldn't believe that I could be responsible for it. What did your mother think, Tony? Was something similar?
I think Shirley might think
Yeah, Shirley was the same reaction. Anyway, the people in the lab keep it extremely clean, and we keep all the mine dust out of the many experiments we have there. And so in 2012, Stephen Hawking came back again to see where we are and what we're doing next. Absolutely remarkable individual. The most remarkable thing about Stephen Hawking is he did all of his good work after he had his disability. And when he got to us in 2012, the only thing he could do was twitch his right cheek to stop the words on his computer that scroll across in order to form a sentence. So I stood there for about 3 minutes waiting for him to simply form the sentence, "When does it start?" talking about one of our experiments. And yet he just continued to do it very patiently. And I think probably it's a sense of humor that helped him throughout his life, as well as a strong curiosity. Sense of humor, when he gave a talk, he was talking about the cosmic microwave background, 2 degrees above absolute zero, that's 290 degrees below 0 Celsius. Almost as cold as Sudbury in the wintertime, as he said at the time. So we get our inspiration in many ways, and these days the inspiration to try to understand our universe comes with light, and we're going to go over to Ellis Hall and have a look at a telescope that does that next. I've told you about neutrinos. Radio waves, there are different types of telescopes, but they're similar to light in their nature, electromagnetic waves. And they give us tremendous information about farthest reaches of the universe and unusual objects like black holes. Gravitational waves, the last 5 years or so, there's been remarkable developments in observing effects of gravity that come in the form of a wave that we can measure when 2 black holes come together or when neutron stars come together. And we're learning a lot as we go forward. And so astronomy has become a multidimensional and a multi-messenger, as we call it, science. And so stay tuned about that. In the meantime, let me, with Connor's help, you're going to see a light telescope. Let's just take a little trip underground and see what it's actually like to go 2 kilometers underground to study the sun. So please go ahead.
Your visit to Snow Lab starts in the early morning at Creighton Mine, near Sudbury, Ontario. The surface building hosts offices, laboratories, and support services. It's here where you begin to gear up.
Turn the volume down just a touch.
A name given to the shower and change rooms. It's here where you change into your clothes for underground, normally shorts and a t-shirt.
That's good.
As the temperature underground can easily reach the mid-30s. Over this outfit, you must wear a set of mining coveralls, waterproof safety boots, a hard hat, safety glasses, and a mining belt. All this gear is required to travel safely down into the mine. Everyone entering the mine must tag in so that there is a record on surface of who's underground at all times. The final piece of equipment you need before heading underground is a cap lens. The battery pack attaches to the mining belt, and the light attaches to the front of the hard hat. You join other Snow Lab staff to wait for the cage, the large elevator that brings people and materials to and from the surface. It's a tight squeeze as you descend 6,800 feet, over 2 kilometers, in just a few minutes. You experience 25 to 30% more air pressure at that depth, and the descent feels similar to flying in an airplane.
40 kilometers an hour.
Snow Lab is located at this depth to shield sensitive experiments from the cosmic radiation at the Earth's surface.
Takes about 3 minutes to go all the way to the bottom.
Once arriving at the 6800 level, watch your steps as you enter the drift. The drift is the main part of the mine. It's important to keep your path lamp on and to watch your steps during the 2-kilometer walk from the cave to Snow Lab. Snow Lab is a clean lab, meaning dust and dirt must be kept to a bare minimum. Mine dust, in particular, can interfere with experiments if it gets into the lab area. For these reasons, strict cleanliness protocols are in place. Everything that enters the lab must be thoroughly cleaned. That includes people. The first step is to wash the mud and dust off your boots before entering the lab doors. As you step into the lab, you notice a temperature change immediately. The conditions in the lab are well regulated to keep a constant temperature and humidity. At this point, everyone must remove their hard hats and belts and hang them on the hooks along the wall. Remove your boots and safety glasses and place them on the shelves. Remember where you placed your boots. The next step is to head to the underground drive. Upstairs for women, downstairs for men. There is a dirty side and a clean side to the drive, separated by showers. Anything that has been in the drift must remain on the dirty side. To ensure the lab stays as clean as possible, everyone showers to remove any remaining dust that may linger on skin or hair. You are provided with safety boots, a t-shirt, and clean room suit following your shower. These outfits remain underground and are washed in laundry facilities in the lab to eliminate the possibility of getting contaminated by mine dust in traveling to and from the surface. You also need to wear a hairnet, safety glasses, and hard hat in the lab. As you leave the dry and enter the lunchroom, everyone must tag in again to keep track of who is in the lab. The lunchroom is the heart of Snow Lab and also functions as the lab's refuge station. In case of an emergency, staff and visitors would congregate here. Scientists, staff, and visitors will spend 8 hours underground, working on experiments, building the newest areas of the lab, and maintaining the facility. At the end of the day, you and the rest of the Snow Lab crew pack up and head back to surface. The Snow Lab crew will be back, prepared to do the same thing all over again tomorrow.
Are you the microphone tosser? This is the microphone. Oh, that one. Do you use this one too?
You can use that. I've never used it before.
I thought this was fun. This is one you throw. Whoever wants to.
Safety hazards.
You're right. You're right. I don't know. Use that one. Does anyone have a question?
We'll take a few questions. Yes. Once. There.
What is sprayed over the ceiling of the clean lab that looks like some kind of white spray? Is that actual rock surface that's been sprayed to cover to keep the dust down?
Yes, I think it's epoxy paint, is it not, Tony? In the
Layer of shotcrete first and then the epoxy paint. The shotcrete is a special cement that they use that keeps the stability stability of the rock so you don't have any shards or anything falling down. And once you've got that coating on, you can add this paint, which is an epoxy paint. Yeah.
In the chamber itself, in order to be water and radon tight, we used Uralon plastic, which was developed here in the mining engineering department actually to keep, your basement gets radon from uranium in the soil. And here, it's kind of the ultimate basement. And so what they did in the mining engineering department was develop this coating made of Uralon that makes it possible to keep in uranium mines, where it really is a problem for the miners breathing it in, keep the radon coming out of the walls to a minimum so they can then flow fresh air from the surface through. But it was perfect for what we wanted. It lowered the amount of radon getting into our detector by about 100,000 times. So very useful. Anyone else?
I just wanted to ask, are the neutrinos that you're detecting all originally from our own sun, or have some of them come from another star?
Well, that's an excellent question. The answer is that the ones in the energy range we were looking at are dominated by the ones that come from our sun. The nearest star is so much further away that there are many fewer of those. But there are other neutrinos that are produced. In fact, the other half of the Nobel Prize went to a measurement made in Japan to Takaaki Kajito, who was the leader of the Super Kamiokande experiment, which used neutrinos that are produced by those same cosmic rays that produce the northern lights. In the atmosphere, there are neutrinos produced that were used for their measurements. And in very extreme objects, black holes, for example, you can have enough energy to produce neutrinos. And the ice at the South Pole has been instrumented. A kilometer of ice cube, a kilometer in each direction of ice at the South Pole has been instrumented with light detectors to observe neutrinos coming from outer space. Very high energy is all that they can observe. But they recently observed a neutrino that appears to have come from the same location as something that a number of other astronomical instruments observed. And it was a prime example of this multi-messenger astronomy that I'm referring to. So yes, there are all kinds of different energy neutrinos, but ours are dominated by the sun and the region we were looking at. Okay, next question after this comes from someone.
My question is, why isn't this no lab underground in Ontario?
Okay. I was going to say the next person should be under 15, but why is Snow Lab underground in Ontario? Okay, first of all, it's underground because there are particles that are bombarding our atmosphere, and that's what makes the northern lights, that would make our detector glow. And we can't afford to have that happen because we only see one faint burst of light from a neutrino an hour. And so we can't have a glowing detector, or it would make it impossible to distinguish those faint bursts of light from neutrinos. The reason it's in Ontario is that we were fortunate to have, well, first of all, people like George Ewan here at Queen's who went looking for the best underground location back in the 1980s and found the site and someone in the management of INCO who was willing to allow us to be situated there. And that is one of the deepest mines in North America and one of the best places, therefore, to do this sort of work. Hope I answered your question. Yeah.
Hi, Professor. I want to ask a few small questions. And first question is about...
One question, and then we'll go to the rest of the audience. Pick your best one.
Okay, no problem. And the more questions I will ask about after the speech. And the most important question is why we need the Stone Lab, and how does this to benefit our daily life? Like something like electricity will bring us some iPhones, computers, and I don't know how does Stone Lab to benefit our daily life, and why we need the Stone Lab.
So you really think iPhones benefit our daily lives? But I'm sorry. Let me take your question very seriously. First of all, we're understanding the laws of physics at a very basic level. I mentioned the fact that we also made measurements that may give us a source of energy that is non-polluting compared to many of the sources we use today. Those are two examples. However, it turns out that whenever you push the boundaries of basic science, you learn new technologies as well. It kind of goes back and forth. As the basic science improves, the technology improves. As the technology improves, you can do the basic science better. And so the improvements in technology that we have seen have been, by and large, as a result of people understanding, for example, how a transistor works, and then how to, in case of an iPhone, how do you get many of them in a very tiny chip, and on to where we are today. But the science of understanding what happens when you have materials such as those that make up transistors behaving in the way they do in an iPhone was what started the whole thing. And so basic science is of value for technology as you go forward as well. I hope I answered your question. Thank you. Yeah.
I was wondering what makes heavy water better than regular water for the purposes of the...
That's an excellent question, and I passed over that in the interest of generality in my talk. There's an extra neutron inside inside the hydrogen nucleus in deuterium. Electron neutrinos come in and strike that neutron, and they produce a fast-moving electron, going faster than the speed of light in water. Now, you may say nothing goes faster than the speed of light. You'll learn in your physics texts eventually that your glasses don't work if you don't have a change in the speed of light inside the glass. In this case, it's going faster than the speed of light in the material water. That produces light. That's very distinctive for an electron neutrino. But any neutrino type can just knock the neutron out. And when it knocks the neutron out, we have a free neutron in our detector, and we had 3 different ways of detecting those free neutrons. And the number of those we observed told us how many of all 3 types were present in our detector. So we had one measurement for the neutrons of all 3 types, and one measurement specifically for electron neutrinos. And they're only 1/3 of the total were electron neutrinos. The other 2/3 are changed into the other types, participating in the reaction that knocked out the neutron, but not participating in the one that made the light by going faster than the speed of light in water. So that was why this heavy water specifically was what we needed. It's very expensive to separate it out of normal water. That's where the 300 million comes in, but that's why we used it. Thank you for your question. Yeah.
Just to follow that question up, I don't imagine you're using absolutely pure D2O. Which is how pure do you need to purify the deuterium?
Well, this was 99.75%, if I got it right, Tony. What was right? 99.82. Okay, 99.82. We had to make sure we didn't give it back any worse than 99.75. Did I get that right? Okay, and we didn't. So that's how pure it was in terms of the ratio to ordinary water. And the problem we would have, for example, if we had ordinary water in there, is that second reaction I described a moment ago, where you're just producing a free neutron, they would be captured in that ordinary water and do something that we would not be able to observe compared to being free to go and be detected the way we detected them. So it was important.
Check your sights.
Hi.
Why do we only get 1 neutrino per hour found?
I'm sorry, could you say that again? I didn't quite catch.
Why do we only found one neutrino per hour?
Why only one per hour? Well, because, okay, so I told you there are billions of them going through us at any moment. But only once an hour in this enormous tank of heavy water, it's goes across this room and almost filling this room with heavy water. Only once an hour did a neutrino did it hit the nucleus of an atom. Because you'll learn in school that atoms have a nucleus and then electrons that go around the outside, and they're mostly open space. And so it went through all the open space most of the time. Once an hour, it found one nucleus and it hit it head on. And that's when we saw a burst of light. And so that's why it was only once an hour. I hope I explained it. It's tough, but it's a good question. Yeah.
How long did it take to build the snow lab?
Snow lab in particular, that took about 3 years, Tony? Roughly 3 years, starting somewhere around 2004. The snow detector itself, where we did the original excavation and we had to do all of this particular construction, took from 1990 until 1998, about 8 years to build before we started doing any sort of operation. So quite a while.
So my kind of question is pretty related to that one, actually. If these neutrinos can travel through a light year worth of lead without hitting anything, and we'll have one in our body in a lifetime, how is it that you guys are able to capture one every hour, kind of on the other side?
Well, it just turns out that we knew what the probability is for them to interact with an atom of deuterium. And we knew how many atoms of deuterium there were in our detector, and we knew, because that's what we were testing, the numbers that were being produced in the core of the sun. And so you put together the numbers that are being produced with the distance you are away and the number you have there, and you do a calculation of what the rate is. And that came out to be about 1 an hour. So.
All right, last one.
How do neutrinos change?
How do they change? Oh, that's a really big question. But it's a really good question. It's very difficult to explain it to you except by using what's called quantum mechanics, which you won't study until at least grade 8. I'm fooling. It's something that you study in your 3rd year or 4th year of university. So it's very complicated. But let me try. When a neutrino is produced, an electron neutrino, it's produced in one of those reactions in the sun that also involves an electron. So you know it's that type of neutrino. But it turns out that that type of neutrino is not just one single mass. It's a combination of 3 masses, we think. And as it travels, it changes. The process of traveling changes how much of mass 1, mass 2, and mass 3 is represented by that thing that was produced in the sun. And when you make a measurement, as we do in our experiment, the way quantum mechanics works is you have a certain probability of observing the set of 3 masses that you started out with, and a certain probability of seeing the set of 3 masses that makes up one of the other 2 types. And what we measured was that the probability of seeing something that looked exactly like what it started out with was 33%. We only saw them 1/3 of the time. And so quantum mechanics is an unusual subject where you no longer can calculate things exactly. You can only calculate the probability that you will observe something. And that was what applies in this particular case. So I tried to answer. I hope I came close. There is another interesting thing, though, and that is, and this deals with another thing that Einstein came up with. One of his most amazing contributions is something called special relativity, which is an unusual subject that says nothing can go faster than the speed of light. And if they are traveling at the speed of light, then they don't know what time is anymore. If you actually none of us will ever get to travel at the speed of light because it takes an infinite amount of energy to get there. And if we did, our watches wouldn't work anymore. So it turns out that in order for the neutrinos to make those changes, to change from one type to another, they have to keep track of the time and how far they traveled and stuff like that. They do it. And therefore, they can't be traveling at the speed of light. And anything that doesn't travel at the speed of light has to have a finite mass and travel slower than the speed of light. And so there's a simple explanation just using what Einstein discovered back in 1905 or 1910 that explains why if you observe this change from one neutrino to another, it means they have to have a finite mass. And that's what's kind of neat about how science works. You know, Einstein's sitting in his study, writing something down on a piece of paper. He distributes it to other scientists. They look at it, they review it, they say, this sounds right. And now, here in 2001, we observe something that is a result of what he decided back in 1910. And that's what's good fun about science. You can think about things that are written down and valuable to everybody forever and ever. So anyway, I probably made it even more complicated for you. But
all right.
Science is fun. It really is.
All right. Let's thank Art again.